Hi students, I'm your lecturer Dr. Fanman here. So in this episode, I'll be sharing with you some things about ozone. And first up will be how to measure the ozone concentration, right? So if you look at this picture carefully here, the amount of ozone in the ozone layer determines whether you have an ozone hole or not. So imagine the ozone, right, O3 as a triatomic molecule. This is the area that's covered by the column here, right? And this is the thickness of the ozone covered by the ozone, right? So what happens is, right, if you see like this is a slab, let's say you think of it like a cement, right, of 3 mm thick, right? This corresponds to 300 du here, and the du represents the acronym called the Dobson unit here, which is what we use to determine the amount of ozone there. So we talk about the total ozone amount. The column ozone is defined as the total number of O3, right? N3 of molecules of ozone. So this is N total number, right? 3 stands for cubic molecules of ozone in a complete vertical column of the atmosphere of unit horizontal cross section here. So it's an integration of 0 to infinity, because you never know how thick it is, right? Amount of ozone dz. So this is more math, but I won't talk about it much here. But I would like you to know that if you see this picture on the right where my cursor is, so this is the coin. Let me just use the analogy here, right? So if your average reference value of the ozone around the world is about 3 mm, which correspond to 300 Dobson unit, so our ozone hole would be classified if the thickness is about 1 mm. Okay, so it's all relative. We take this as a reference because it's a global average here. So the convenient way to measure the ozone column is really by the du Dobson unit, and this dimension is about the height or the thickness of the ozone in the column, and we can talk about it as if we can cool down ozone until it is a standard temperature and pressure, which is your 1 atm and 0 degrees Celsius. Okay. So you see that now we have a transitional thickness of the ozone hole, or how thinning of the ozone layer, from the 1970s all the way to 2013 here, right? So you notice that what constitutes ozone here is that the ozone hole is the depleted region of the ozone enclosed by the line with a constant value of 220 Dobson unit. Now this value of 220 du, right, is chosen because the total ozone values of less than 220 Dobson unit were not found in the historical observations over the Antarctica prior to 1979. You see that here, after 1979, there was a globe of blue area, right? You see this part here of 220. So there's a bit of variability of the ozone layer. In order to pitch to you this question here, why was it chosen, and I've explained. So want to summarize this: a hole is not really like a gap, like a cavity. There's no ozone, but just a comparative thinner ozone amount compared to the other values. So the thickness of this ozone does depend on a couple of factors. It depends on the photochemical and the dynamical conditions, and therefore there can be very large variations in the time and space, and their origins can be very natural and anthropogenic. Now the next part is we talk about the dynamics of the ozone hole here. So the thickness of the ozone layer varies with time, as we've seen just now, right? Because as the human progress here, we generate some kind of CFCs here, and the chlorofluorocarbon does break down some ozone to a certain extent. So this thickness of ozone varies with time, right? And the figure here below shows that the measurements of the ozone that's performed by the RMI UCO. Now the red line, and the green line here are measured by the daily values for the year and the last year, okay, for this year. And the black line represents the mean value, right? Represents the mean value derived from all the measurements performed since 1971. Okay, so 95% of all the observations are in the shaded region, and the day-to-day variability can be as large as the 20%. It means that the thickness of the ozone layer can change by more than 20% in a day, right? And what it means is this variability is also larger in winter and spring. You see that? There's more variations in winter and spring. But in the summer, the gap in the gray zone is narrower. Now, the other important fact is the annual cycle. So on average, right, the thickness of the ozone is greater in March, right? Somewhere in March here, right? Higher amount of ozone, right, in April, and lowest in October and November. And this cycle is related to the general air circulations in the stratosphere in the different seasons. So the thickness of this ozone, or the ozone content, is measured specifically using design instrument called the spectrophotometers, and is expressed in the DU. We talked about it just now in the previous slide. And a layer of 0.01 millimeters thick of ozone at 0 degrees Celsius and 1 atm pressure here, which is 101.325 Pascal, is defined as 1 DU, the Dobson unit. And if the ozone layer, right, if the ozone layer over our region is compressed to about 0 degrees Celsius here, it will be about 3 mm thick. So in the previous slide, we see the coin, right, 3 mm thick here is about the compressed version of this ozone. Okay. Now, since we know that the thickness of the ozone, right, varies with seasons and locations on the Earth here, and the ozone is created naturally in the middle and upper stratosphere of the tropics. So due to the high availability of the UV radiation there, you see that the Earth is round, right, and this part here gets the most amount of the light here and the heat, right? So the ozone is created more in this part, okay? But the thing is, atmospheric circulations, or we call it the Burrow-Dobson circulation, transport the ozone from the tropical source region to the extratropics, such that under the normal circumstances, right, the thickness of the ozone is larger at the higher latitude and lower at the lower latitude. Like for instance, this larger ozone concentration is usually found in the northern Europe, Canada, Siberia, near Russia, than above the equator. So this is the equator, right? So you see closer to the northern part here, you find a higher amount of ozone. And you see that the global view of the ozone, right, that the color represents the thickness of the ozone. You see here towards the pink color side is very thick. You see yellow is also very thick here, but the blue is really just the ordinary part. And below the equator to the southern hemisphere, it is not so thick, right? So one can clearly see that the ozone is thinner along the equator right here, the thinnest among everywhere, north or south, right, and thicker above the North Pole. So this can be explained by the fact that the transport of ozone is the strongest during the late fall and winter, right? Because remember the figure just now shows the distribution, of the middle of January in the northern hemisphere, because of this prominent topography and the more pronounced land-ocean contrast in the northern hemisphere. So what I'm saying is, right, you see the northern hemisphere, there's more contrast between the land and the ocean, but at the bottom, at the southern hemisphere, is primarily more ocean than the land. Okay, so you might want to know where is Singapore here, right? Do we get a lot of ozone? Little red dot here. Okay, so to learn more, I would like you to take a look at this website and see. We call it the NASA Ozone Watch. I think it's really interesting to look it up here. And I'd like to pitch to you a question here. What is the trend on these changes of the ozone hole for the last week? You just go, it's instant, it's live, and then just do some data analysis. I think it's very interesting. So I'll continue next class. Cheers.